Thank you for the introduction. Wen Jie from Zhejiang U, and today I will talk about the two-party computation for transformer inference. The background is very similar for the Nexus. When using the AI servers, sensitive information have to be sent to the server, and it will raise some privacy issue, like the data may be potentially exposed or mismanaged. So the question is, how can we use the AI servers without leaking, without sending out our data, or the input and the model? And beside the fully homomorphic encryption, in the previous, the first talk, and there is another option, like using secure two-party computation. Generally, secure two-party computation has two parties, each provide their private input to the function, to the protocol, and they run interactive protocols. At the end of the protocol, they can get a result, and in the middle of the protocols, all the messages are encrypted or secure sharing, so they achieve some privacy and correctness. And one of the most important building blocks is to generate correlated randomness, like multiplication randomness and the AND gate randomness. And besides the client and server setting, I want to distinguish ourselves from the two other variants. In those variants, they rely on an assumption that a trusted party, like in the left, and the third party, and the fully trusted party can generate the correlated randomness and distribute it to the two parties. And for example, it can be done using a secure hardware like SGX. And it is very active research. There are many related approaches in these recent years, and most of them are based on additive secret sharing, except the Sigma. They use functional secret sharing, and they use different 2PC library, and it lead to different security model. Like some of them are in the TFPs, the trusted first-party assumption, and some of them are under the TDP assumption, and other are just pure two-party setting. And currently, they support different transformer like BERT only, or in Shaft. They can support the model written in PyTorch, and like Oakland. Our BumbleBee can support model writing in JAX. And because some of them have to replace the component of the transformer, so some of them have to run a model fine tune. And some of them are not preferring model fine tuning. And our observation is very easier. Like for the current approach, most of them have to introduce a tremendous communication, might be hundreds of gigabytes just for one token inference. And the second observation is the computation cost is particularly cheaper than the communication. If you're just checking the Amazon on demanding prices, you can find out that communication is pretty expensive. And our goal here is we want to some kind of minimizing the communication without introducing too much computation. Like from our approach under the lab bottom, and we reduce the communication like by 1/10. And the computation running time is just a little bit shorter. And we are basically facing three issues here. The first is to design protocol to evaluate nonlinear activation function like JLU and softmax in the two-party setting. And some of the previous approach had turned to 2PC friendly alternative, but we will harm the accuracy. And some of them, the other of them had to turn on very fancy numerical approximation, but actually it introduced a lot more communication. And the second issue is is from the engineering side. Like we have to facing two kind of methodology. The first is let the machine learner to write the cryptographical code, or let the cryptographer to write the machine learning code. And the third one is to design a two-party computation protocol for the large-scale matrix multiplication. As a contribution, we have different lessons learned from this project, and which I will give more details. And we provide end-to-end code base for the whole private transformer inference. Like we can just download the JAX code from Hugging Face and no more model fine-tuning and just run. And technically, we present an approach for doing matrix multiplication using homomorphic encryption. It is some kind of fast, but it is for just one multiplication. It's not that used in the DEXs, which is support multiple matrix multiplication. For this, it's just for one multiplication, and then we interact for the next matrix multiplication. But it's a concurrent work by Jiaxin in this year, in the previous year CCS. So I will leave the detail in the papers, and you can check out the URL code in our GitHub. And what I really want to share is 3 lessons we learned from when doing this project. The lesson 1, I would say, is let the machine learner to write the machine learning code and to transfer the machine learning code to the secure computation using some kind of compilers. Because for the large transformer, it's really hard to write from scratch, and there's tons of Python code already in the Hugging Face. Why not we just reuse them? And a better way, it should be used some kind of compiler to transfer those Python code to a two-party computation backend, which is done by 3 Shaft, Sigma, and BumbleBee. And but the way we done is different. Like Shaft is some kind of Python level overwriting, which is some kind of ego execution. And the second one, and the BumbleBee, we use some kind of middle layer IR to transfer the Python code into a graph, and then execute the graph. We prefer the middle layer IR, and we will give you one exact example why we prefer this middle layer IR. Here is some piece of code for computing softmax in the Hugging Face code and in the very common Python code. For the softmax is the formula there. Basically, we are computing an exponential and division, but the divisor is just one scalar, and the division is a vector. And the issue is the keep dimension true here. It's very common code used by machine learner to align the operand shape. However, it will increase the cost of division by maybe 10 or 100 times because of we expand from one scalar to a large vector. A better way, it should be replace. If a computation graph is possible, and we can rewrite the IR before we execute them. Like we can replace the division by a multiplication and add one inverse before we do the multiplication. So the number of multiplication is the same, but we reduce the number of inverse into just one inverse. And actually, it's quite a sad story that some of the previous work will identify the softmax as the bottleneck of the whole private transformer inference because of this kind of the division, the decision. But actually, in our work, the softmax is only takes less than 1% of the total cost. Actually, not it's never being a bottleneck for the transformer inference in the 2PC setting, actually. And the lesson 2 is we tried many numerical approximation, but we find out the piecewise, the simple piecewise approximation is better, is suitable for our cases because of the numerical stability. Like, for example, The J function is some kind of scary, but if you just plot the see the plot, it's kind of how to say some kind of linear in the two sides, and just a little curve in a very short range over the origin. And the variance is just for the easy computation. It's almost the same. And we try many attempts, like we numerically approximate the hypertangent, but which required the input has to be laid in a proper range, so we have to do the clipping. And the division here is really expensive. And we also try some kind of Fourier series approximation to approximate the hypertangent. Like in my old paper, we have a very efficient protocol to evaluate the Fourier series. But the number of modification here is quite lot because we have to do 8-degree Fourier series, so we have like 18 modification. Yeah, the attempt tree is also the same. So it's time to we're thinking the simple piecewise approximation. For the piecewise approximation, like we can come up with two optimization. One is the one versus many comparison, like because the input is just 1 point, and the comparison here is one signature versus many plaintext, which can be combined together and we evaluate with a much more better efficiency. And the smooth, I just skip the smoothness. And lesson 3 is simplicity is actually good. It's also about the numerical stability. Like for the softmax function, generally we have to compute the max first as minus the max and then compute the exponential. And at this point, exponential on the negative inputs are bounded. It's really easier to approximate them with just low degree Taylor series. Just like we do a degree 3 Taylor expansion, it will give you a very pretty good approximation on the negative input. And then in the bottom, we can just use one more clipping, because for that input, the exponential is just becomes almost 0. And because it looks so simple, and some kind of maybe some of them you will see, okay, it's too simple. Why not consider a fancy numerical method like in that paper? And the good thing for this recommendation is that it's division free and maximum free. But however, for numerical method, we have to make sure the input is in the proper range, which requiring rank clipping. So it's actually not that good for this simple case. Actually, for the softmax, we just do one max maximum, and compute a very low degree Taylor series. Thanks. And I will have to talk this joke. Actually, it's the true motivation in my heart why I want to do this project, because many years ago I have a paper named Cheetah. It's doing almost the same, but for the neural network. And when it comes to transformer, like I'm very nervous for the very transformer. At the first beginning, I come up with this naming. I want to name this new project as Cheetah, because Cheetah plus transformer is another transformer. It's a very almost 13 years animation back then, but my team leader said Cheetah is so unknown. Let's become BumbleBee is more famous. That's it. Thank you.
Wenjie for sharing his lessons and insights. Anyone would like to ask a question? Yeah, I like the name. Yeah. Great.
Thank you for your amazing work, and I am really surprising about the performance for the nonlinear computation in your work. And I am a little bit curious about how was because the nonlinear computation in your work is involved the approximation with the interval containment, right? And I'm curious about how it was really, how the interval containment was, or the secure comparison was implemented in your work. Because from my experience, such approximation-based method with many intervals to be determined was empirically cost in secure computation. So
Yeah,
I am
yeah. The
a
question
little bit
is how
curious.
to do a batch of comparison efficiently.
Yes.
Yeah, just check out my Cheetah paper.
Okay.
Yeah, exactly.
Okay.
You two would like to discuss more offline? Okay, thank you.
Thank you.